Ini bisa dimulai atau gimana Mbak Yasar?
Iya, Pak. Sudah bisa dimulai, Pak, sambil nunggu yang
Oke. Yang pertama berarti ini ya, apa namanya? Indonesia Raya.
pembukaan itu sama Pak. Iya, pokoknya
Iya,
dari Pak Pat.
oke. Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Okay.
Morning.
Uh, Before we start
Assalamualaikum, morning.
this webinar, I would like to introduce my name. I am Fadhan Bafi. I'm researcher in Research Center of Mineral Technology BRIN. And today we have two presenters. One is Dr. Zheng Mi from RMIT University, and second presenter is Mrs. Ulin Herlina from Research Center of Mineral Technology BRIN. And for before we start the webinar, maybe we will listen Indonesian national anthem first, and then second one, there will be opening remark from the head of Research Center of Mineral Technology, Mr. David Chandra, and then we'll start for the first presenter and then the second presenters. Okay, that's the agenda for this webinar. We can go to the first agenda. Maybe Mr. Aceh, Pak Aceh, can you help? Okay, thank you. For the second agenda is opening remark from the Mr. David Chandra as the head of Research Center of Mineral Technology. Time is yours.
Okay, thank you very much, Mr. Fatan. Uh, I want to clarify, I'm not the head, and just represent ya. Jadi saya bukan kepalanya,
Oke,
hanya
Muhammad Giri.
mewakili Pak Fajar. Oke, thank you very much. Uh, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi semuanya. Good morning and best wishes to us all. Distinguished speaker, moderator, Vero Rexi practitioner, academic, and the committee of the dissemination event. Yang terhormat ya buat para narasumber, moderator, para praktisi akademi dan eh, tim ya, tim dari webinar diseminasi ke-6 ini. First of all, I want to express our gratitude to God Almighty for the opportunity we can gather in this webinar. Pertama-tama saya ingin mengucapkan rasa syukur ya kepada Tuhan Yang Maha Esa, Allah Subhanahu wa Ta'ala, atas kesempatan kita bisa berkumpul ya, kita bisa sharing knowledge di event webinar ke-6 ini. And first, I want allow me to introduce myself. My name is David Chandra Birawida. I'm one of researchers in the Pusat Riset Teknologi Mineral. I'm here representing the head of the Mineral Technology atau Pusat Riset Teknologi Mineral, which is Mr. Fajar, who is unable to be with us today. Nah, jadi perkenalkan ya, nama saya adalah David Chandra, salah satu peneliti di Pusat Riset Teknologi Mineral. Dan izinkan saya di sini saya mendapatkan kehormatan untuk mewakili ya Bapak Fajar ya, di mana beliau ada berhalangan hadir karena ada tugas ada rapat ya, ada rapat mendadak, kebetulan kemarin malam harus pergi ke Jakarta. And on this occasion, I want to express our deepest gratitude to our speaker ya, Dr. Jang Mili. Hello, Dr. Jang Mi. Thank you for your time. And second, Ibu Ulin Herlina. She's our colleague in PRTM, the Pusat Riset Teknologi Mineral. Then the moderator, Mr. Fatan. Yeah. Hello, Mr. Fatan. Thank you for guiding today's discussion. And the committee and all of attendants which give their time to present in this webinar. Jadi pada kesempatan kali ini izinkan saya untuk menyampaikan rasa terima kasih yang sangat besar ya kepada para narasumber yang telah bersedia meluangkan waktunya untuk sharing ilmu dan pengalamannya. Kemudian moderator juga ya, kemudian ada tim dari webinar dan juga para hadirin sekalian yang telah meluangkan waktunya. Ladies and gentlemen, the purpose of this webinar is to share knowledge and insight on mineral technology. And we hope today's discussion will be beneficial and can bring our progress for all of us. Jadi tujuan dari webinar kali ini pada intinya adalah sama dengan webinar yang sebelumnya. Jadi untuk kita ngobrol ya tentang mineral ya, ilmu mineral ya, share knowledge ya, dan siapa tahu bisa memberikan insight bagi kita semua. Dan saya harap ya bisa diskusi ini memberikan keuntungan ya yang besar bagi kita semua. And of all, let's enjoy the event, and I hope we have a fruitful discussion ya. Jadi mari kita meriahkan diskusi ini dan semoga diskusinya bisa positif. Wassalamualaikum, sekian dari saya. Wassalamualaikum warahmatullahi wabarakatuh. Oh ya, mungkin saya mau pantun sebentar ya. mendadak ini. Jadi I want to give a welcoming poems. This our tradition in the webinar, and I hope Mr. Moderator will give two poems ya, will two poem good poems I think. So. Oke, jadi pergi ke pasar membeli rotan. Rotan dibawa naik perahu. Selamat datang para undangan. Semoga ilmu yang didapat penuh berkah. Terima kasih.
Cakep.
Okay. Thank you. Thank you, Mr. David,
Oh ya nggak apa-apa.
for the opening remarks. I think I will prepare for the poems. Maybe in the last, I will give the book after this webinar. Okay. Before we start, maybe Mrs. Lisa, we need to take photo together, or yes, Mbak Lisa.
Thank you, Mr. Fatan.
Yeah.
Please on camera and virtual background. Oke.
Untuk semuanya tolong nyalakan
Kamera dan
kamera
aktifkan
dan
virtual background yang telah kita share di chat room. Ya. Slide pertama. 1, 2, 3. Smile, please. Thank you. 5 minutes. Slide kedua. 1, 2, 3. Oke. Terima kasih.
Oke, thank you Mbak Lisa ya. Terima kasih Mbak Lisa. Oke, so after finish this agenda, so we will go to the first presenter. Jingmi, are you ready for your presentation already?
Yes, I'm ready
Yes.
for the presentation. So, could I share the presentation slide?
Yeah.
Could I share the presentation slide right now?
Yes, yeah.
Yep,
Okay.
sure.
Okay, Jingmi, the
Yep,
floor is yours
sure.
right now.
Thank you, Fatan. And it's my great honor to be invited to this webinar. Thank you so much, Fatan, for inviting me to this webinar. And then my name is Jangmi Lee, and then I'm working at RMIT University in Australia. I'm not sure like how many of you guys have visited in Melbourne, and Melbourne is beautiful. And then if there's any chance, I highly recommend to visit Melbourne one day. And then I also would like to visit Indonesia one time if there's any chance. So yeah, I'd like to continue this collaboration in a positive way, and then to build up more, the research topic working together. So basically this research that I'm going to present today is basically what myself and also Dr. Suno Lee, who joined this webinar, working together. So, and the title of this presentation is Mechanistic Insight into Redox Controlled Dissolution Pathways in Laterite Ore System. And yeah, let me just like briefly introduce our university. We call as RMIT University, but the full name is Royal Melbourne Institute of Technology. So yeah, there are campuses like in the city. Fatan has visited to here last year, and the city is really crowded and then full of people. So the space is not that spacious. So we have another campus 1 hour, half minute away from the city, which is really spacious, and kangaroos is running around. And then, yeah, there are spacious campus as well. And then we also have campus in Vietnam as well, and the Europe campus. And then it's really, I would say, like global university, I would say. And also we have a lot of state-of-art facilities that is really beneficial in conducting the research. And also there are so many very supportive technical staff. And then we are pursuing really multicultural environment. So many people from the diverse cultural background are living together in our university. So it's really good place in terms of the cultural and societal and research effect as well. And next, I would like to introduce briefly also about like the center that I'm working on, which is the Center for Advanced Material and Industrial Chemistry. And then we call it simply as CHEMIC. So in CHEMIC Center, this center is pretty big, and then it's been led by the distinguished Professor Suresh Bhargava, who is really old professor, but he's still really passionate in conducting the research. So yeah, we are under his umbrella at the moment, and then he's leading this center together. And then within the center, there are so many disciplines, and which is basically related to the energy applications. So as you can see here in the right side, the nanotechnology and sensing and molecular engineering and food technology. And then there is a resource utilization and also critical mineral sector. So Dr. Suno Lee and myself are working in the critical mineral sector at the moment. And there are core members who are working in the different disciplines within the center. And we've been driving and trying to drive the innovation in mining and mineral sector for last couple of 10 years. And we've been working on the uranium and copper extractions and also rare earth metal extraction, but sorry, not extractions, rare earth metal, the ores beneficiation we've been working on. And also we've been also working on the nickel extraction and cobalt extraction from laterite ores. And then also we are currently working on the recovering the valuable metals from the e-waste and secondary resources. So we have, as an outcome, we graduated like 16 PhD students who is right now working in the relevant critical mineral sector like ICOA and CSRO and PHP uranium like that. And also we've been collaborating with many Australian mining companies, including like a BHP and ICOA and Rio Tinto as well. So yeah, in our center, we've been really actively working on the critical mineral sector, I would like to say. Yeah. So jumping into the research topic of what I'd like to present today, I'd like to, before discussing the dissolution mechanism or extraction mechanism that I'm going to present mainly, it's useful to briefly consider the geographical profile and current processing approaches for nickel laterite ores. So the laterite, as you know really well, the laterite deposits are typically vertical stratified system. The upper limonite zone is rich in iron oxyhydroxide or oxide and generally contains moderate nickel and cobalt concentrations. In contrast, the deeper saprolite zone contains higher nickel grade, but significantly lower cobalt content. Because of these mineralogical differences, the different processing route can be applied to each zone. Saprolite ores are commonly processed with the pyrometallurgical route, such as smelting. But these processes are highly energy intensive and require significant capital investment, and also it sometimes do not efficiently recover the cobalt. On the other hand, the limonite ores are generally treated using hydrometallurgical pathway, like a high pressure acid leaching, like a HPAR, but it's really effective in extraction of nickel and cobalt, but HPAR operate under really highly corrosive conditions. It requires substantial sulfuric acid consumption and generate large volume of acidic tailings and also neutralization sludges. So through these challenges, and also in order to develop like efficient and sustainable extraction method like pathway, it needs to improve the understanding of dissolution behaviors in that laterite ore system, particularly how mineral phases respond to chemical and redox conditions during the leaching. So actually, basically this research has been conducted based on the collaboration with our industry partner, and who is QPM, Queensland Pacific Metal. And then we've been received the ore from them, and then the ore was coming from the New Caledonia, and then they are actually constructing the pilot plant in Brisbane within the Australia. And we are collaborating based on like what they want to figure out in terms of the fundamental aspect when leaching or when solvent extraction, something like that. And then they ask us to do like some fundamental research, and then we conducted here, and there are results like that. And then based on the really constructive discussion, they employ the fundamental aspect into the pilot system. So that's how we collaborate with this company in the last 4 years. So basically, this is the flow sheet that they are employing when they are establishing their pilot plant. So you may know really well about the nitric acid leaching. So this is about the atmospheric nitric acid leaching. So I am mainly in charge of like this nitric acid leach. And then they want to figure out like how this nitric acid will be converted into like reactive nitrogen species, and then how we could improve the leaching efficiencies of like especially cobalt and nickel and manganese from the laterite ore that they are utilizing. So yeah, and the beauty of this flow sheet is like we can recycle the nitric acid solution, and then this will be fed back to the fresh nitric acid leach. So nitric acid is more expensive as compared to the sulfuric acid, but in this flow sheet, we recycle the nitric acid, and then we can, make the closed loop when we are extract the critical metals from the laterite ore. So the laterite is, as you know really well, laterite is inherently really multi-phase system. It contains like a lot of goethite or hematite and or asphalt, manganese oxide, and the cobalt is the co-associated with manganese and sometimes iron, something like that. It's really inherently multi-phase system. However, redox perturbations do not affect all mineral phases uniformly. For example, manganese oxide domains are really highly redox sensitivity, because normally manganese exists as a 3+ or 4+ high valent oxidation state, and iron oxyhydroxide, mainly goethite domains are comparatively stable within the investigated redox range. So the redox shift selectively destabilized the manganese hosted domain, fundamentally altering the dissolution sequence. So why the redox matters in process condition? So under nitric acid condition, the redox reactions are unavoidable. the nitrate reduction generate nitrogen oxide species like a nitrogen dioxide or nitrogen monoxide species as a gas type, or other, they can so much generating like reactive nitrogen species, particularly at elevated temperatures, and also this shift the OIP of the system. So this introduces the electron competition reaction. The electrons can be consumed by the nitrate reduction, or electrons can be consumed by the manganese and cobalt reduction to its soluble 2+ oxidation state of the manganese and cobalt. But in contrast, the iron oxyhydroxide, like I mentioned in the previous slide, the coesite dissolution remains largely governed by the proton-promoted mechanisms under the same condition, nitric acid condition. So therefore, the redox perturbation does not merely like accelerate the dissolution kinetics, it modifies the sequence in which the mineral domains destabilize and dissolve. So from the processing perspective, this distinction is really important, I personally think. So the gap in the current understanding is it has been really investigated, the numerous like kinetic studies for laterite ore dissolution, the activation energies, and also like kinetic models, and yeah, many like the rate determining steps has been proposed. However, the most of these kinetic models and like activation energy calculated and the rate determining steps treat the system as a bulk reactive, as a whole bulk system. So the phase-specific destabilization under redox perturbation is rarely resolved, and I think it will be important to figure out the linkage between the ORP variation, the reductive capability, and the dissolution and destabilization of the critical domain, and yeah, sequence would be pretty much important in later on. So this leads us to the core research questions of this work. How do redox perturbations selectively destabilize the manganese hosted domains, and how does this selective destabilization govern the overall dissolution pathway in laterite ore system? So by doing so, we try to bridge the macroscopic leaching trend and kinetic interpretation and atomic scale structural evolution into a like unified framework through this study. So before conducting the leaching test, we would like to characterize the laterite ore that we'll be utilizing for this research topic. And like I say, like this laterite ore is coming from the New Caledonia, and then it has been sieved under 300 micrometer, and then humidity level is below 2%. Oh, so sorry about that. I put the XRD pattern in this area, but like yeah, I was somewhat confused about like the other version of the presentation slide. That's my mistake. So sorry about that. So
No problem.
so sorry. And as you can see here in the TMU's characterizations, we made a calibration curve, as you can see here in the cobalt and manganese. So with the well-known oxidation state of the metal oxide that was purchased from the Sigma Aldrich. And then we made a calibration curve through the TMU's characterization. And then after checking the manganese and iron and cobalt nickels signal through the TMU's characterization, and then check the ratio of L2, L3, and L2 peak. And then we we went to this calibration curve again, and then we could figure out what is the oxidation state of the manganese and cobalt. Because like through the XPS, because the content of the manganese and cobalt, manganese can be detected, but cobalt is really tiny amount. And XPS is sort of like bulk characterization, so it cannot be detected through the XPS to figure out the oxidation state. So that's the reason why I chose this TM yield characterization to locally figure out the oxidation state of the cobalt. So through this TM yield characterization, we could figure out like cobalt exists as +3 and manganese exists as a +4 mainly. And also through the XRD, through the XRD, the main phase is about the goethite crystal structure, iron oxyhydroxide, and then secondary phase was quartz phase, silica. And then through the XRF characterization, this contains like 0.33 weight percent of the cobalt, and iron is 45.3, and manganese is 1.4, and nickel is 1.65. So this is just over characterization of the laterite ore. And we've conducted the macroscopic dissolution behavior under the atmospheric nitric acid condition. So let me briefly explain about the condition. This is the atmospheric nitric acid condition. And then actually we've added the additional reductant, and then reductant we use, as you can see here, this is the ferrous iron. We use ferrous iron as a reductant, and then the other reductant, nitrite iron, we use. So two types of the reductant we use for this research. One is ferrous iron and nitrite iron. So the temperature at which the reductant, and also like, as you can see here, the reaction proceeded for 6 hours. 6 hours, and reaction for 6 hours will be proceed at 110 Celsius. But what we make different in each condition is like adding of the reductant temperature. So we added the reductant and ore at the same temperature, but different temperature between the test. So we added the temperature, we added the reductant and ore from 70 to 110 Celsius, and then increase the temperature to 110 and then maintain for 6 hours. That is the reaction condition. So as you can see here, when the reductant was added at lower temperature, especially like between 70 to 90, manganese and cobalt leaching efficiencies become higher as compared to the 100 Celsius and 110 Celsius. But however, when the reductant introduced like the higher temperature, 100 and 110, higher temperature of addition of reductant, lower leaching efficiencies of manganese and cobalt. And I didn't upload the leaching efficiencies of nickel and iron in this slide, but in case of the nickel and iron, it didn't show much difference depending on the adding temperature, which is unlike to this manganese and cobalt leaching efficiency. So this finding is like, from this finding, we can tell like maybe like the nitrogen, when we add the reductant, it generated a lot of NOx gas because it can reduce the manganese and cobalt, but also it can reduce the nitric acid solution. So they are competing reaction. So when they react more vigorously with nitric nitric acid, the less amount of the reductant will react with the manganese and cobalt from the laterite ore. So as you can see here, this is the photos right after of adding the reductant at different temperature. So you can see this reddish brown color, which is the nitrogen dioxide gas, and it may also include like nitrogen oxide gas. This is the result of the reduction of nitric acid solution. So as increasing the temperature, the reddish brown gas evolved more. So it may indicate at higher temperature, after adding the reductant, the nitric acid reduced more, and less amount of the reductant reduced the manganese and cobalt from the laterite ore. So we would say this is because of the competing reaction. And we also check the oxidation and reduction potential variation across the leaching. We monitored in situ ORP measurement during the leaching process. And in bare nitric acid at 110 Celsius, the ORP normally ORP can be measured like a 1,200 something like that. This is normal, like the bare nitric acid solution at 110 Celsius. As you can see here in both of the ferrous iron and nitrite iron, when the reductant is added, you can see the drop of the ORP value, which is indicating the creation of the reductive environment when we added the reductant. And when we add the reductant at lower temperature, you can see more drop of the ORP value, as you can see here. So the lower temperature means more reductive environment creation. But there is a difference between the ferrous iron and nitrite iron, which is like in case of the ferrous iron, like once we add the reductant into the nitric acid solution, temporarily it drops the ORP value, but quickly go up and is stabilized across the 6 hours of leaching test. It stabilized at the like a same ORP value as bare nitric acid solution. It quickly go up and then maintain just normal ORP value of bare nitric acid solution. But on the other hand, the nitrite ions case, at lower temperature, when we add the nitrite reductant, it drops the ORP value, as you can see here, and it go up, but depending on the addition temperature, in case of this 70 Celsius, as you can see here, it still remain really low ORP value as compared to the bare nitric acid solution. So as increasing the addition temperature, it go up, it saturates higher ORP value, and eventually at 110 Celsius, it looks pretty much similar with the bare nitric acid solution. So we assume that in case of the nitrite ion reductant, maybe like nitrogen species chemistry is really complex. So in case of the ferrous iron will be converted into the ferric iron, and then it can release the electron to the manganese and cobalt, and it can reduce into the soluble form, which is the divalent oxidation. But in case of the nitrite ion, it's not like simple process as like ferrous iron. So it will react with the nitric acid more complexly, and then it can generate like very variety of reactive nitrogen species like a HNO2 or HNO or NO2 minus and NO minus, and so many complex, and then it all involves into the reduction of like nitric acid, also the manganese and cobalt oxidation state. So we are still figuring out like which species are mainly affecting and then which species are minor affecting, and then reaction pathways that we are still figuring out, which is really complex. So if you guys have any idea, we can do the collaboration in this field as well. So yeah, and then we've done the kinetic study at the different temperature. The previous leaching test is like just make a difference in terms of the addition temperature, but all the leaching tests for 6 hours were done at 110 Celsius. That was the criteria, that was the requirement. The reason why we fixed the leaching temperature at 110 Celsius is, I told you this is the industry collaboration, and 110 Celsius is sort of like optimized condition that our industry is considering to apply to the pilot plant. So we fix, in previous leaching tests, we fixed the leaching temperature as 110, and then we just make a difference in terms of the addition temperature of the reductant and ore. But in order to conduct the kinetic study, we have to see the leaching behaviors at the different temperature, not fixing the leaching temperature at 110 Celsius. So this study is conducting the leaching test at different temperature for whole 6 hours between 50 to 110 Celsius. And this condition is without reductant, just nitric acid solution and adding the ore, and then to see how it goes. So this is basically the acid-driven dissolution, because we haven't used the reductant for this study. And then you can see here all of the like metal like a cobalt and manganese and nickel and irons are temperature dependent. But as compared to the nickel and iron, the cobalt and manganese are somewhat limited in terms of the leaching efficiencies. When reductant introduced, like we had used like 2 types of reductant, as I mentioned, like ferrous iron and nitrate iron. And sorry, I didn't label the graph. So the left side is about the ferrous iron, and then the right side is about the nitrate ion. So when reductant introduced, the dissolution regime changes a lot as compared to the leaching test under the absence of the reductant. The manganese and cobalt extractions are strongly enhanced when we use the reductant, especially at the early stage. And this is consistent with the redox-triggered destabilization of manganese-rich domains. However, increasing temperature does not monotonically increase this enhancement. Under the ferrous iron condition, as you can see here, the reductive effect diminishes at elevated temperature in early stage due to the accelerated reductant consumption for the nitric acid solution reduction. But in case of the nitrite ion, ferrous iron diminishes a lot as increasing the temperature, but nitrite ion still, there is a competing reaction with the nitric acid reduction, but still, even at 110 Celsius, it shows like more sustained reductive environment, allowing more prolonged manganese-coupled dissolution. So we've conducted the kinetic study under the absence of the reductant and under the condition of the reductant, and using this data, we conducted like congruent dissolution of nickel with ferrous, with nickel from the iron and manganese phase. So the assumption of this study is that like nickel is existing mainly from the iron phase and also manganese phase. So we are assuming that manganese phase in this laterite ore is mainly asphalt crystal structure, which is the manganese oxide crystal structure. So through the other characterization, which I will show you in the later presentation slide, that we are expecting like manganese oxide is the asphalt crystal structure, and cobalt, some major portion of the cobalt is co-associated in the asphalt crystal structure, the manganese oxide, and also some portion of the nickel is co-associated at the manganese oxide crystal structure. But major portion of nickel we are expecting from the iron phase, goethite phase. So based on the assumption that the nickel will be dissolved from the iron phase and also manganese phase, we did a congruent dissolution study based on the previous kinetic study, the leaching test to see the kinetics. So we did a bit of like regression. We did a regression equation, and then we found the nickel dissolution follows the dual host of iron phase and manganese phase coupling, and then across the all temperature, nickel dissolution can be described as linear combination of manganese and iron dissolution. And this is the table that we've done estimate the regression coefficient of each from the manganese phase and iron phase. And then actually this is the amount of the nickel leach gram. This is not the leaching efficiency. So we do the mass normalization, and then we calculate the mass normalized contribution. And as you can see here, the 70 to 80% of nickel dissolution is associated with iron phase, and like around 20%, like 90% to 27% of the nickel dissolution is associated with the manganese phase we found. So, yep, so this occurs to all temperature, and regardless of the reductant used, we found like nickel is distributed in this way from manganese phase and iron phase. And to validate this regression dried host phase distribution of nickel from the iron phase and manganese phase, we perform the nickel KH exubs validation. So this is the nickel KH exubs data of the initial laterite ore. And then this is exub data, and then we did a fitting using based on the two different crystal structure. So when we did a fitting, we put the two different crystal structure, which is the iron oxyhydroxide and manganese oxide site. So we put two mixed crystal structure and then see how it goes. And then you can see the nickel and iron scattering paths at here. This means nickel is associated at the iron phase. And then you can see another scattering path, which is the nickel and manganese. The nickel-manganese scattering path means that nickel is co-associated in the phase of the manganese oxide, which is the asphalt lane. So we did a fitting, and then you can see the coordination factor at here. So depending on the coordination factor, we would be able to estimate the percentage of this scattering paths, nickel and iron, and nickel and manganese. So these were estimated, like this estimated that like 70 to 80% of the nickel is from the 70 to 80% from iron side, the graphite crystal structure, and also the remaining 20% is from manganese side. So this result is quantitatively consistent with the regression model that this one from the congruency dissolution. So yeah, this is another EXAPS study and X-ray absorption spectroscopy study of the laterite ore. So yeah, this is the cobalt and this cobalt KH, and this is the manganese KH spectra. And this is all like SR. Let me explain about the left side first. So this is the left side is about the initial laterite ore. And then we just compare with the reference materials with the different oxidation state. So as you can see here, in case of the cobalt, the laterite ore is showing pretty much on the similar position of the 3+ oxidation state, lithium cobalt oxide, and or this one. So which indicating the main oxidation state of the cobalt exists in the laterite ore is mainly 3+. And as you can see here, the manganese KH, in case of the manganese KH, the manganese from the laterite ore exists mainly +4 because the position of this laterite ore is very similar with the delta MnO2, which is the +4, and also cobalt doped delta MnO2. So we confirm through the TMLs and also this X-ray absorption spectroscopy, we confirm both characterization confirm us that the manganese and cobalt exists as a +4 and +3. And at here, we also check cobalt graphite. So if the cobalt is located in the graphite crystal structure, the spectra looks a bit different as compared to the cobalt in the asphalt crystal structure. So in our case, it looks like a cobalt is really locating in the asphalt crystal structure rather than graphite. You can see the difference at here. And in manganese case as well, manganese also mainly locating in the asphalt, and that's really obviously. But in case of the cobalt, it's really challenging to check the EXAPS range. Because like their cobalt is really tiny amount in the laterite ore system, and then there is the interfering of signals of iron, which is really large abundance in the laterite ore. But I will do the synchrotron study, which using the spatial spectrometer, which can eliminate specifically the iron signal, and then we can get really accurate cobalt signal from the X-ray absorption spectroscopy. So if you want to do some collaboration in this way, let me know, and then I will be able to check like cobalt KH EXAPS signals through that. And this is the SR. I mentioned it here is the solid residue collected after the leaching test. So after the leaching test, like mainly the Jane's spectra remains the same, but I didn't show the result in this presentation slide, but in the EXAPS signal, it shows a bit of like the disorder factor increase. So after the leaching, we found like the creation of the oxidation vacancy and also increase of the disorder factor. So this is the summary. The laterite behaves as a redox differentiated multiphase system, and then the iron bearing phases is mainly proton-driven dissolution, and manganese bearing phases is strongly governed by the redox sensitive system. And so redox conditions modify the dissolution pathway rather than like increasing metal speciation. And nickel dissolution follows the dual host coupling from the congruent dissolution, and then we found like from 70 to 80% is from the iron phase, and the 20% of the nickel is from the manganese phase, and then nickel host phase distribution. This distribution was also confirmed by the nickel KH XF signal through the feeding with the two different crystal structure. And yeah, so through this study, I would like to integrate like kinetics and congruent dissolution and XFs, and then it may provide some insight in terms of the mechanistic framework for the redox controlled laterite processing. Yep. So thank you so much for listening my presentation, and then I would like to acknowledge like our center team members and also Queensland Pacific Metals, my industry partner, and also yeah, I'd like to thanks to Fatan again for inviting us. And also, yep, the industry partner that I'm working with, I'd like to acknowledge. Thank you so much.
Okay, thank you, Jengbi.
Thank you.
Yeah, maybe I forget to introduce you. So Jengbi is a research fellow from RMIT University. So I'm working with and also with Sunho. So they are couple, I think, in the RMIT. So I mean, their research talking about the selective metal extraction from laterite. So, and maybe rare earth, maybe in here also we have rare earth research group. So maybe in the next, maybe we can talk about that one.
Yep, sure.
And then for the ask and question session, maybe in the after the second presenter, Chengmi.
Okay, sure.
Yeah.
No problem.
Maybe could you to
Stop share.
Yeah, stop share for that.
Sure.
Okay. Thank you, Jengmi.
Thank you.
Okay, waiting for in here. So we will listen for the second presenter. Okay, for the second presenter, Bu Ulin. Okay, floor is yours. Waktu dan tempat silakan, Bu.
Okay.
Sebentar, Bu. Yes. Before I will to introduce again, I forget again. So, the second presenter is Mrs. Ulin from Research Center of Mineral Technology BRIN. So, his topic right now is about low-grade chromite sand beneficiation and processing strategies for ferrochrome raw material preparation. So please for the attendance, so you can send you can listen for the second presenter or for Mrs. Sulin. Floor is yours. Thank you.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Mr. Fatan, for the introduction. Let me share my file first. Yes, I will share my PPT. Bismillah. Okay. Is it okay? Okay. Bismillah. Okay, thank you, Mr. Fatan. Today I want to share our research about chromite. It's about low-grade chromite sand beneficiation processing strategies for ferrochrome raw material preparation. This is our research in the last 2 years in BRIN. I'm sorry, it doesn't move. Oh, yeah. Okay. There is our team from BRIN, Universitas Indonesia, and also Institut Teknologi Sumatera. I would like to thank for my team for the support and teamwork, for Mr. Bambang Suharno, Mr. Fajar Nurjaman, Mr. Laode Arham, Mr. Anton Sabto, Mr. Fatan Bahfi, Mr. Triswan, Mrs. Yuhelda, and Mr. Ijang Suherman. And then our college, Mr. Ridwan, Mr. Shahrezi, Mrs. Febriani, Mr. Rain, Mr. Calvin, and then Mr. Erickson. I would like to thank you for your support and the teamwork. This is our research focus, how to utilize the low-grade chromite sand as a raw material for ferrochrome production. This research has three parts. First, how to increase the chromium content in chromite sand through a physical beneficiation process to separate the impurities that are not directly bound to the chromite compound. And then the second, how to increase the chromium content in chromite sand through thermal beneficiation, such as a reduction roasting process to separate the impurities that are directly bound to the chromite compound. And the last is how to optimize ferrochrome smelting using DC arc furnace from low-grade chromite sand resulting from beneficiation. Inshallah, I would like to do the last focus in this year. Bismillah. Chromium, as known as chrome, is a chemical element that has a symbol Cr and the atomic number is 24. Chrome is found in the mineral chromite or chrome ore. Chrome always used in combination with other materials. So chrome contributes unique qualities such as corrosion resistance, good performance, resilient to extreme temperature. There are two classification or two categories of chromite. First is commercial and the second is non-commercial. The non-commercial has low content of chromium trioxide. It's below 25%. And then the use of chromite is for metallurgical grade. This is the highest grade. Usually we use it for ferrochrome. It has 48% of chromium trioxide, and the ratio of chromium to iron is up to 3. And the middle grade is sodium dichromate. The content of chromium trioxide is up to 44. And then the ratio of chromium to iron is 1.5. And then the low grade is refractory grade. The content of chromium trioxide is around about 30 to 40%. Ferrochrome is used as raw material for stainless steel. Stainless steel contain about 8% chromium in stainless steel type 3 or 4. The use of chromium in stainless steel is to produce corrosion resistant, mechanical strong, heat resistant, and hard-turning stainless steel. The classification of ferrochrome, first is the high carbon ferrochromium. It has chromium content up to 60%. And then charged chrome is about 50 to 60% chromium. And then medium carbon ferrochrome is 56 to 70% chromium, and the last is low carbon ferrochromium is about 56 to 70% chromium. This is the challenges in a smelting process. First, about raw material. High-grade chromium or supply have become constrained, implying that the need to utilize low to medium-grade chromium resources. And then how to utilize of low-grade chromite to achieving the quality and yield needed for ferrochrome production. And then the last is how to optimize the process parameter. The parameter is such as basicity, and then the content of carbon is essential to achieving a high metal yield and chromium recovery during the smelting. This is the distribution of primary and placer chromite resources and reserves in Indonesia. Most the potential chromite has located in Sulawesi, Kalimantan, and then Nusa Tenggara Timur. And then this is the material I use in this research, chromite sand. It's from Morowali, Central Sulawesi. The grade of chromite sand is very low because the chromium content is 8.5, and then the ratio of chromium to iron is only 0.9. In SEM RDX mapping, we can see that there is the element that separate, and then separate or not directly bond to the chromite compound, and also it has impurities that directly bond to the chromite compound. So this chromite sand has to pass the beneficiation before we process to ferrochrome. This is our preliminary study, how to smelt the chromite sand as ferrochrome. The chromite sand with various flux and then various carbon, it has low chromium content. The chromium content is only about 40%. And then this is the effect of the flux in the chromite sand smelting. And then it's the effect of various coke addition. It's also the content of chromium. It's only about 45%. So this primary study that exceeded slag achieving by edit silica flux has produced the highest metal recovery in basicity 0.6, chromium recovery. The result is 83.26%, and the metal yield is 16%. And then the adding 20% stoichiometric coke as a reductant improve the reduction rate. The result is metal yield 90 98%, and then recovery is 98%, and then the metal yield is 80%. The resulting product, it has chromium with 40% content chromium, and then 46% of iron. It doesn't meet the stainless steel industry's requirement because the industry needs ratio of chromium to iron is up to 3. But this product only the ratio is only 1. So it is necessary to concentrate the chromate sand using methods such as physical beneficiation and then thermal beneficiation to enhance the optimal chromium to iron ratio. Next, we go to the beneficiation. First, the beneficiation is about physical. The objective of this beneficiation is to separate impurities that are not directly bound to the chromate compound. It has two kind of beneficiation. First is gravity concentration, and then the magnetic separation. I use a shaking table to separate the impurities from the mass of the material, and then I do the magnetic separation to reduce the Fe content or ferromagnetic impurities that not directly bound to the chromate compound. The optimal result of this physical beneficiation followed by the thermal beneficiation. It uses a reduction roasting process to separate impurities that are directly bound to the chromate compound. And then the last is analysis. What is the product of the beneficiation? This is the result of physical beneficiation. I use two parameters in this physical beneficiation. First is about the inclination, and the last is water flow rate. The chromium to iron ratio is improved in this physical beneficiation. In inclination 7.5, and then the water flow rate is 18 liters per minute. This is the same. Then the XRD of the physical beneficiation. Oh, the content share ratio is improved from 0.9 to 1.62, and then the chromium content from 8.5% improved to 20.77%. This optimal result, and then followed by the thermal beneficiation. This is the result of thermal beneficiation. I use several parameters. such as additive and reductor, and the last is temperature. The optimal is in temperature of 100 and 300 Celsius degree. The additive, the base is calcium silicate, and then the reductor is coke in 7.5%. It shows that the iron is formed, and then the iron is separated in magnetic separation. So the impurities of the iron will be separated from the chromate element. And the result is the best result is this chromium to iron ratio is improved from 1.62 become 44.2, but the chromium is decreased. It's about 80%.63. So this is the conclusion that the low-grade chromate sand is not recommended to directly smelt in an electric arc furnace because the chromium content and the ratio of chromium to iron do not yet meet the specification expected by the industry. Physical beneficiation utilizing a shaking table effectively separates impurities which have lower density than chromate, such as silica, calcium, magnesium that found in minerals. This process increased the chromium content from 8.5% to 20.4% with a chromium to iron ratio of 1.90. And then the tube in magnetic separation improve the chromium to iron ratio to 1.62 with chromium content of 20.7%. And the last is thermal beneficiation has improved the ratio of chromium to iron to 4.2. Okay, thank you. This is the last of our sharing session. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Awesome. Thank you, Mr. Sulin, for your nice presentation. So we will go to the next agenda is ask and question session. So if there is any question, you can raise hand, or maybe you can write in the chat. Room. Is there any question? Oke. Ada yang mau bertanya? Ini di chat room tadi ada yang bertanya tapi belum bertanya dari Al Jalali. Oh ya, ini ada yang raise hand. Ya, Lukmanul Hakim, you can ya
Yeah, thank you so much. Hi, everyone. Sorry for my camera. There's a problem with my camera. I was just wondering, thank you for the interesting presentation from both speakers. For Dr. Jami, I was wondering about the heterogenic electric system. So how can you distinguish between the direct reductive dissolutions and the secondary dissolution? For example, like for the direct reductive dissolution, we use like it can occur which triggered by like bacteria or the organic agent. For the secondary dissolution, it can be triggered by the release of the ligand or the ligand exchange. How can you like how do you distinguish between those two mechanisms? And then do you have any kinetic study about those mechanisms? And the second one, it's about uh, the mechanism of the redox reactions. Like for example, like in the redox transitions, normally it can happen in the microscopic scales in the pores. And then how can you give like a bridge between the data that you obtain from the laboratory and the ones that you get from the field because of the dynamic hydrological dynamics that can affect it by the water flow or the oxygen, which will never achieve the equilibrium thermodynamics. So can you give like how did you bridge the data gap between the study you conduct in the laboratory and the one that you get from the field, which can affect by external factors? Thank you.
Okay, thank you.
Yep. Thank
Sarma. Okay.
Thank you. So
Okay,
so
Zeni, yeah,
yeah,
maybe, maybe I will give sorry, can you hear me?
can you hear me?
Yeah, can you hear me?
Yes, I can hear you.
I will
Yep.
take all the question first, and then maybe after that you can directly answer after that. Maybe I just give okay, you can ask. You can answer after. Maybe there is another question. So I will collect all question first, and then
Yes.
maybe after that you can answer it.
Okay, so I
okay.
can't remember.
Oh, you can remember. Okay.
Yes.
Okay. Maybe you can directly to ask. Sorry, you
Yeah,
can directly to
so
answer for
yeah.
the question. Yeah.
Yeah, so I already forgot about the first question. So
The first question is how to
yeah.
distinguish between the mechanism of the your mechanism, that one, and also how about
The
the
primary dissolution and secondary dissolution.
Yes, and then also the kinetic mechanism for that one. And the second one is the redox is how to your process for the redox can happen in your research.
And second question was
For the
redox.
redox for that one is not actually happen in the hydrometeorology, right? So how you can explain control for the maybe like the external effect, like something like water or something like that. Sorry, like
Yeah, water.
yeah.
So yeah, I mean like the first question was about the mechanism, how to distinguish between primary dissolution and secondary dissolution, right? And the primary dissolution. So I mean like the Lukmanu.
Lukman. Maybe Lukman, can you repeat again for the first
Oh,
one?
yeah.
For
Yeah.
the mechanism for distinguish between the mechanism, the redox,
Yeah.
and also
So
Yeah,
are you
Yeah, for
also
yeah,
are you also working on the laterite ore system?
not really. So that's why I just wondering because this is something new for me. I just want to
Yeah.
know like because in the redox transitions, it can be triggered even by the real ligand exchange or ligand
Yeah.
release, or maybe
Yeah.
by the bacteria or the organic agents. Like how do you distinguish between those two when you conduct this kind of research? Do you have any kind of genetic study about that, like maybe how fast, how good, how efficient, something like that, when you compare between the primary dissolution and secondary dissolution?
So I mean like I don't it's yeah, I just like thought about like the redox reaction because it's really obvious in this laterite ore system that is like the manganese and cobalt to be reduced and then it is really governed by the redox reaction. And in case of the iron phase, it's like a hematite, of course, like it is not actually governed by the redox reaction and goethite as well. So I actually haven't looked at this one as like yeah, I haven't divided like into actually from the primary resolution and secondary dissolution. So I'm just confused like the what is the primary dissolution and secondary dissolution, to be honest.
Mm.
So I mean like there is a specific of my interest in the dissolution, especially in case of the 3D transition metals like a nickel and cobalt and manganese and iron. Of course, there is a chromium and magnesium and aluminum and silicon and bit of like zinc as well. But I mean like what I mean like how we can divide into like primary dissolution and secondary dissolution. Yeah, to be honest, I haven't heard about the primary dissolution and secondary dissolution. So I mean like how to say I'm to be honest, I don't know how to say about this.
Okay. Okay, maybe
Yeah,
yeah, Lukman.
it's okay. I mean, because mostly I think if I'm not wrong, it just when you do this kind of study, it's mostly about the ligand exchange, something like that, or you use a
So
kind of
yeah, I mean like the ore is really really different. I mean, like in case of the nickel also can be like co-associated not only in iron phases and but also the other silicate phases, nickel can be co-associated. In that case, like I heard like the ligand exchange can be applied in that case, but in this system, like it's mainly depending on the acid-driven dissolution. And if we use like reductant, the redox reaction will be involved in case of the metal dissolution. So yeah, as far as I'm aware, like in this system, like ligand dissolution, ligand exchange mechanism is not not I mean like how can I say like yeah I didn't think about the ligand exchange in this system, to be honest.
yeah, because that's the secondary dissolution that I mean. The one that you explained, I think it's like a primary dissolution that you use you use the system. So because in the redox process, the ligand exchange also have a kind of different impact compared to the study that you conducted that you use like a primary redox reactions. So in the mechanistic study, sometimes we found like a different like mechanism in terms of the efficiency, something like that, or maybe like the kinetic study when you use like a ligand exchange, or the
Mm,
or the primary dissolution, like you use like organic agent or something like manganese or something like that. There's a kind of like a different efficiency that you can get, like how it's affect the acidity or something like that, because the fluctuative pH also affect how fast the both systems, like even in the secondary or in primary. So there will be a different mechanistic study if there's a fluctuative pH during those process. So that's why I was wondering about this kind, because my background is a chemistry. So I like a redox process. So there's a kind of like a pH, fluctuative pH really affect those two mechanisms between the primary and secondary. And the one that you explained is the primary one. So for the ligand exchange, I want to know how it's applied to the laterite process, like, because I don't really have experience about the laterite, but I just know a little bit about the redox transition process. Yeah, thank you.
Okay. Okay, thank you. So yeah, I mean, like, it's really good question, and then your question makes me like to look into, like, think about the secondary phase, like secondary dissolution, other than like first, primary dissolution. Thank you so much. Thank you.
Thank you.
And
Thank you, Lukman.
yes,
Yeah.
there was a second question as well,
Second
right?
question, yeah, for that one.
I have a question.
Yeah.
Yeah.
Bentar Pak, masih ada pertanyaan yang tadi sebelum. Okay, for the second question is redox is happening in the, I mean, how you can explain for the redox happening in your research? Maybe I think same.
So, I mean, like, yeah, I'm not sure this could be the answer, but like I told you, this is an industry project, and then like I'm sort of like mimicking what they want to do in terms of the leaching test as a bench scale at here, and then they are right now constructing the pilot plant. But actually in the real system, like, they don't add the reductant. They don't add nitrite ion. They don't add the iron species. So, but the reason why I'm using this reductant in this bench scale is, like I told you, like in the QPM flow sheet, as I introduced in the presentation file, they use atmospheric nitric acid solution, and they can recycle the nitric acid solution. They can regenerate the nitric acid solution from the leaching test, and then they can put into another leaching test after regenerating nitric acid. So that's what is that is the beauty of this flow sheet, because they can't, they don't need to buy every single time. They don't need to buy brand new nitric acid, which is really expensive. But in case, what they found is, like, when they regenerate the nitric acid, and then when they put that regenerate nitric acid into the new leaching system with the new ore, what they found is, like, a cobalt and manganese leaching efficiency has been so much increased. So we are assuming that, like, in the regenerate nitric acid solution, there might be some impurity, or there might be some reactive nitrogen species that can facilitate the redox reaction of the cobalt and manganese. So it's really interesting. So they want to see, like, the fundamental aspect, and they want to figure out, like, which nitrogen species are affecting on primarily the manganese cobalt reduction. So like, yeah, so in bench scale, even though I'm adding like reductant for ferrous iron and reductant of like nitrite ion, but it's a bit tricky to apply as it is to the pilot system, because adding this reductant would be really costly, and then they can't achieve like the leaching efficiency that I achieved through the bench scale into the pilot system. So there is a bit of like difference between bench scale that I'm conducting and the pilot system that they are constructing at the moment, I would say.
Okay. Okay, maybe we are going to the second question. I mean, from the second from Al-Jalali, Bapak Al-Jalali.
Yeah.
Nah,
Yeah. Did
hanya
you hear me?
Oke,
Maybe directly to the presenter, Dr. Jan Mili.
oke. Ya, Pak,
Yeah.
silakan.
Thank you so much to the organizer. Yeah. Dr. Jan Mili, thank you so much for your nice presentation in today. Maybe I have a question. In your process, you have precipitated hematite, right?
Precipitated hematite. No, goethite.
Oh, goethite. But
Yeah.
can you show me your process? Please show me again your slide process. Yeah.
GPM process, I think. GPM process that.
Oh, KPM process. So yeah. So yeah. Okay. I will continue to my question. The other question again. Please show me again the result from nickel leaching recovery. The dependent of the temperature and so on. Please.
Can you share maybe your presentation before Jamie?
Sorry. Let me share the
Yeah.
presentation slide first. Sorry. So here,
Yeah. Nickel leaching recovery.
this one. Nickel
Yeah,
leaching
and the other one, the
recovery.
other slide. Yeah. Yes.
This
The
one, right?
leaching
Flow sheet.
efficiency of nickel. No, the other one. I
The
think,
other one.
yeah, the other one, please show
This
me.
one. Kinetic study.
No.
Halaman berapa, Pak?
Yes, for nickel.
For nickel.
Yeah, nickel recovery. This one. Yeah. Okay, thank you.
This one, right?
Well, yes, this one.
Yes. Okay.
Yeah, thank you so much for this. So firstly, I want to say so sorry because my voice, a little bit problem, but I effort for this discussion. So I want to ask you that the nickel recovery, it means the nickel recovery, right? Leaching efficiency.
Yes.
Yeah.
Leaching extraction. Yep.
Yeah. So I understand about that. So
Yeah.
this is very low temperatures from 50 up to the 110 degrees Celsius. And the question is, how did you control the temperature?
How do I control the temperature?
Yes. Because
Using
the information
temperature
if temperature
controller.
is, temperature controller, right?
Yes.
What kind of thermometer do you use? Because the information of temperature is very important for our climate. Yeah, in this process, you successfully found nickel recovery about maybe 83% by the temperature application 110, right? Degrees Celsius. Yeah. And you use the goethite, you use the limonite, I think.
Yes.
Yeah, you use limonite. We know well that in the limonite, the nickel is joined and goethite.
Yes.
FeOH make FeNiOH, and I also study about the kinetic process, a combustion process of the limonite, and I found that the composition of the limonite is from 150 up to the 300 degrees Celsius to decompose this mineral to be maybe NiO and Fe2O3 and release the water. It means to find the nice reaction with the acids may be good if 300 degrees Celsius, right? Because in this temperature, all of the mineral was decomposed to be NiO and Fe2O3. And NiO maybe will bond the acid and make the salt, nickel salt. So we can easily get the nickel ion, I think. But in your process, you just only use 110 degrees Celsius for 6 hours. Can you explain to me, so very low temperature, why the nickel successfully, you can successfully leach much amount of nickel up to 185% of nickel recovery? Thank you.
Thank you. So
Thank
the
you.
first of all, like this is not iron 203. This is not hematite. This is goethite. So
Yeah,
my
yeah,
understanding is goethite is a lot easier to be dissolved as
yeah,
compared
right.
to the hematite.
Yes,
So nickel is co-associated in the goethite
yeah,
crystal structure.
and the goethite, yes, yes,
DCC.
yeah.
Yeah, so I checked another type of ore that has major like hematite crystal structure, but in this under the same condition it shows completely different result. So I think like the iron phase is important as well.
Mhm.
And also, I mean, like this atmospheric nitric acid leaching is
Mm.
very, I mean, like nitric acid leaching is very, very good for nickel extraction.
Yeah, but in your process, what temperature, what condition? It mean atmospheric condition or maybe how much pressure?
No, there is no pressure.
Yeah,
I
atmospheric
think
condition, right?
yes,
Yeah,
yes.
yeah. It's mean, but you successfully found in low temperature, 110 degrees Celsius, you successfully found 85% of nickel recovery. I mean, why? I explain about the goethite firstly. Why? Because nickel associates in the goethite, right?
Yeah,
And
majorly. Yeah, major.
yeah, and the goethite will be decomposed at 150 up to the 300 degrees Celsius, right? Yeah, according to our report, also report for this process, mechanism process. Yeah, it mean we can easily get nice reaction from acid and the nickel oxide in that temperature in the range of 150 and 300 degrees Celsius, right?
So
And in order that we can get much amount of nickel recovery, but in your process just 110 degrees Celsius. Maybe you can explain the process or the reaction mechanism why in low temperature you can found much amount of nickel extraction.
Okay, maybe like that, Jengmi. You mean, I mean, he means like about how you can get the nickel very easy in the
Low temperature.
low temperature 110
Yes. So
because
it's the climb is
So,
very
I mean-
important.
saya jelasin teman ya, ini in the reference.
So, I
he
mean,
said
like, which-
he said
yeah,
in the
which
reference all is in
acid,
the
which
high
acid did you
temperature.
use?
Yes, the
Maybe-
reaction. Maybe you can explain the reaction or the others because this is very low temperature.
Iya Pak, maksudnya
I think-
Bapak pakai chemical apa Pak? Bisa dijelaskan?
Iya. So maksud saya kan seharusnya maksudnya hasilnya ini terlalu gimana ya? Maksudnya bisa enggak dia jelaskan ini barang bahwa dia menghasilkan di low temperature. Seharusnya kan yang kita pikirkan adalah hal terbaik untuk merecovery nikel adalah di temperatur 150 sampai 300 derajat Celcius karena di situ adalah proses dekomposisi dari goethite menjadi NiO dan Fe2O3. Ya, saya pun mempelajari. I also study about this one, about the kinematic reaction and the order and the combustion process.
So,
I
have
also
you
study.
used the nitric acid?
Using same this one, nitric acid also, or
Have you
different?
used nitric acid solution?
I use sulfuric acid.
Yeah,
So,
sulfuric acid
it's
is
very
completely
interesting.
different.
Yeah, no. We don't talk about the difference of the acid, right? But
That's
I just thought
important.
why you can get maybe you can explain the reaction process. Maybe in this temperature, the reaction process like this, like that.
Okay,
Mm.
just explain the reaction process technique.
So,
how
I mean,
you
like
find the nitric acid.
under the nitric acid solution, there is a proton, and then proton attack the ferrous hydroxide, the adjunct of the iron. Their proton attack the oxide in the oxyhydroxide crystal structure,
Yeah.
and then it decrease the, it makes it distort in terms of the crystal structure,
Mhm.
and then they make the bond weaken, and then iron
Yes.
can be released.
Yeah. Okay.
So it's pretty well known that under the atmospheric nitric acid solution, the goethite iron can be released very easily, and then nickel as well. So if you want us to send the patent or everything about like this atmospheric nitric acid leaching, I'm willing to send.
Yeah. Oh yeah, maybe you can send to me the information of this process, because I cannot find well the
So
mechanism process. Yeah.
this has been filed firstly from the CSIRO, which is the Research Institute in Australia. So
Yeah.
this technology has been patented already.
Oh yeah.
You can easily find so many publications related to the atmospheric nitric acid leaching.
Okay.
Right.
Very nice information. Thank you so much. Yes.
No worries.
Okay.
Yeah.
For another question from user.
Kalau untuk pertanyaan kedua bisa Pak?
Oh, bisa Pak. Mau tanya ke siapa
Iya.
Pak? Masih ada?
Untuk yang for the other presenter.
Oh ya, Bulin, silakan.
Iya.
Oke. Maybe
I will
Jengmi, you
stop
can
sharing.
stop
Yep,
share. Yeah.
sure.
Yeah, thank you so much for Mrs. Linta. Bulin, yeah. Jadi, so very nice presentation from ferrochrome, right? But I want to look. Can you show me the XRD pattern, your result?
Ya, bisa di-search.
Okay, wait a minute.
Yes. Your result.
Okay. In this one?
Yeah, thank you so much. Yes, so sorry. Yeah, in previous you presented your raw material include the silica, right?
Yes.
Can you explain to me where's the silica from this peak?
Pardon me, can you repeat your question?
Can you show me where's the silica from this peak, diffraction pattern peak?
Diffraction pattern.
Oh, the pattern
Silica.
of silica.
Yeah.
Oh, yes. Silica in this pattern is
No, there's no silica. Maybe.
Present with this
Oh,
5. It contains
Yeah.
silica.
yeah. Oh, it's the silica join in the product.
Yes.
Yeah. So I think previously you said that this is ferromagnetic. Maybe this is not ferromagnetic, but I think this is spinel ferromagnetic. I think. Yeah. Spinel ferromagnetic, aluminum, chrome, iron, oxide for. But maybe this is just first process from how to get the ferrochrome from the nature. Yeah, but in this process, you just found aluminum, chromium, magnesium, O4. It means this material is very corrosive, right? Not hard, I think.
Okay.
Not hard.
Actu-
Yeah.
Actually, from the thermal beneficiation, we has not the product of ferrochrome. It's only how to beneficiate the low chromate. I want to this so that the first is in how to separate the impurities that are directly or not directly bound to the chromate compound. That is only this two step. The last step is not had been done. So next step, I would like to smelting the this beneficiate this beneficiate chromate. So it the to reach the ferrochrome because chromium is beneficiate. It has a good result in ratio of chromium to iron, so it can be form the ferrochrome which better than before.
Okay. Yeah. So maybe better if you continue this result, because in the first result just spinel, it mean oxide. I think this material is very corrosive. Yeah, we can use directly. Yeah, and include also the silica. It's not separate but join, silica join, just only ordinary combustion process up to the 1,300 degrees Celsius. But the nice process is just ferrochrome. Maybe in the other part, if you have a presentation for the next result, maybe I want to join to look your result. How did you separate and get just ferrochrome hard material? Yeah. Okay. Thank you so much. Just this question. Okay. Thank you so much.
Thank you for your suggestion. Thank you.
Thank you, Pak. Terima kasih, Pak Anjali. Okay. For the another questioner, user who is your name?
Sorry, Mas Watan. That's me, Heru Agung Saputra.
Oh ya, Heru Saputra. Okay.
Okay.
Silakan.
I have one questions for Dr. Lee. Halo, Dr. Lee.
Yes, carry on.
Mana soban kau yo?
Hi. Pak Wan. Oh, panas-panas
So
ini.
actually, actually, I'm wondering about the leaching behavior. Maybe I skip these explanations. So when the use of nitric acid, when you increase the temperature, obviously it will generate more nitrogen oxides. Obviously, this affects to the reduction of the cobalt or mangan. And considering many aspects, actually, what is the optimum temperature for this process in the lab scale optimizations, and whether this optimized condition can be applied in industry scale or not, and also the possibility of using other acids. Did you investigate about this or not?
So
Maybe only that my question.
So yeah, thank you for your question. So as I conducted like this leaching test, we've been done a lot of discussion. What is the optimized condition for this leaching test with the QPM, our industry partner, and like the bench scale is totally different in terms of the configuration to the pilot scale, and then pilot scale, like they need to consider like what is the optimized condition in terms of the economic flow sheet, and then they want to save money as much as they can when running the pilot plant. So actually in my leaching test from the bench scale, adding the reductant, adding the ore, specifically adding the ore in the nitric acid solution at 70 Celsius and then increase the temperature to 110 Celsius was the optimized in the bench scale in terms of the leaching efficiency. But in pilot plant, what they are constructing at the moment is the leaching tank. 6 leaching tanks are linearly connected each other, and they can't actually change the temperature from 70 to 110 Celsius. To decrease the temperature as well, it costs a lot of time and money as well. And the increase from 70 to 110 Celsius, it need money and time as well. So what we found is like 90 Celsius, adding the ore in the pilot plant and increasing the 110 Celsius, which is the leaching test temperature, would be the optimization in terms of the pilot plant. That after a lot of discussion, we found this is the optimized condition, not the 70 Celsius. So there is a bit of difference between bench scale and pilot plant, but they need to think about the leaching efficiency, and also they need to think about the money. So yeah, that's our optimized condition. And there was there any second question as well?
The second question is about the possibility of using other acids, for example, like sulfuric acid. Did you investigate about this on?
So we are just focusing only on the nitric acid, not about the hydrochloric and not about the sulfuric acid. So there is depending on the acid, I'm from chemistry, so I can't think about the bonding. Proton attack to the goethite crystal structure, and then depending on the affinity, it can be easily released, something like that. So depending on the acid, like hydrochloric acid and nitric acid and sulfuric acid, all different. So as Al Jalari mentioned, in case of this sulfuric acid, H-part reaction is based on sulfuric acid, right? So there need to be pressure, and it's gonna be really quick though, but there should be pressure, and then the temperature should be around 250 Celsius, like that. But nitric acid is totally different. It's atmospheric condition, and then myself and industry partners are pursuing atmospheric condition. And then it would be and also we are planning to regenerating the nitric acid, so making a closed loop. So for this purpose, nitric acid is the best option, we think. So yeah, we are in terms of the optimization, the industry pilot plant, and then we are just fixing the acid as a nitric acid. But for the research, I'm open for any acid to figure out or improve the leaching efficiency, or making any new flow sheet using any other inorganic acid, and also the organic acid I'm interested in as well.
Okay, thank you,
Okay,
Jamie.
thank you.
Thank you.
Heru, for the question. And you have another question, no, Heru? Okay.
Enough,
Okay, enough.
Dr.
Okay.
Fadhan.
Okay, maybe because of the time is right now going to 11 AM in here in Indonesia. So maybe in Australia ready for hours forward, right? So I think if there is any question, just one question, I just give the time for one question. There is no question? Okay, maybe I will ask for the interesting for the maybe for Jingmi about the what is the preparation sample for the like I mean this is new for me like hear about the EXAF is EXAF analysis. This one is the very new for for me because EXAF analysis is thing same with the maybe like UVVs or something like that. I don't know for the
Yeah.
yeah
So
this one using the wavelength number or something like that like for the
yeah. So this is also spectroscopy,
yeah
but I mean like in terms of the chemistry viewpoint, there is a metal. There is a metal, and then around the metal there is an orbital, and then the electrons are circulating across the orbital, and then basically the spectroscopy is like we take the electron by irradiating the light and then capturing that electron, and then we read the information. But it's really hard to take the electron from the core because from the core the electron is strongly binding with the nucleus.
yeah.
But there is a synchrotron facility in
synchrotron. Oh, that
Melbourne.
one synchrotron.
Yeah,
Okay,
yeah.
oh,
The synchrotron can generate really, really, really strong electron.
yeah. Yeah,
So
okay.
they can hit the sample, and then it can capture the electron from the really, really core. And then that can give a lot of information in terms of the crystal structure and coordination, and then the sort of factor and everything. So to check, so we normally go to synchrotron to check that characterization. It's only the synchrotron is the only place that we can measure these characteristics. So yeah, and then preparation for this for this measurement is we can check just as a powder type.
Yeah.
Just put the powder on the carbon tape,
Yeah.
or just put the powder, or we can make a pellet,
Yes.
small, very small pellet, and then we can check. And also depending on the the resolution, also we may be able to make a thin film. The quartz on the quartz surface, like we can make a thin film using the powder. So yeah, if you are interested, like yeah, we can have a discussion about the sampling and everything. So yeah, and then we can check
I
together.
think I'm interested about that one for the XF. I think this is same like but different is the solid. For UVVs is like the liquid, right? For that.
Yeah.
Okay.
So in case of the UV visible, like there is also we can obtain the useful information, but this X-ray absorption spectroscopy is totally it will get the totally different information from what we would get from the UV visible spectroscopy.
Yeah. Okay. Thank you, Jane. This is
Thank
interesting
you.
for that one. I
Yep.
think next time we will talk about that one.
Yep.
Okay.
Thank you so much.
Okay. Is there any question for the quiz attendance? If there is any question, maybe I will close this webinar. Actually, right now in Australia is going to evening, right? So before I
It's 3
close,
o'clock.
yeah, before I close this webinar, I want to say thank you. Thanks in advance for your presentation in the webinar, in our webinar. I hope in the next webinar or if you have another your research, you can share with us again, Jimmy.
Yep. Yep, sure.
And also,
Thank you so much.
And also thank you for Mrs. Sulin for your time for presentation in this webinar. So okay, I will close this webinar. Thank you for your attention, for ladies and gentlemen, for your attention in here, for participants. And if you have any question, maybe you can. I will share my phone number if there is some question or PPT. Maybe I will share with you in my WhatsApp. Okay. Okay. Thank you again, Jengmi. Thank you again, Bulin, for the time.
Thank you,
And
Mr.
thank you for the
Fatan.
participant for your attention. Thank you, everyone. Thank you for the committee. Thank you for the represent for head of research now, Mr. David. And I will close this webinar. Bismillahirrahmanirrahim. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and
Assalamualaikum
good
warahmatullahi wabarakatuh.
evening for you, Jengmi.
Thank you. Thank you so much.
Thank you so
Alhamdulillah.
much, Jengmi.
Thank
Jazakumullah
you.
khair.
Thanks,
Thank
guys.
you.
Thank you.
Bye.
Alhamdulillah.
See you, Jengmi. Sunho.
Dr.
See
Jangmin,
you.
thank you.
Bye.
You.
Halo,
Bye.
bye.